Gases. Some things we need to know with gases. Some of the characteristics of gases is that you have low density, which is why most gases float, right? They have an indefinite shape. The shape is going to depend on the shape of the container. So for example, here you have your round bottom flask. Your round bottom flask is connected to your stopcock and another round bottom flask. If your stopcock is closed, your gas is contained in one round bottom flask. Once it's open, the gas is going to run through and come over into the other round bottom flask and completely take up the shape of the container. It has a large compressibility. What does that mean? It can be compressed, okay? And you have moderate thermal expansion, meaning when you heat it up, it's going to expand, okay? Now, pressure, as we know, is a force pushing on a unit area surface on which the force acts. Pressure is therefore equal to force divided by area.
It has a different name? Because
What?
physics is the same name, but chemistry always change the name.
No.
What happened here?
No. No. Okay? Now, when we're working with gas laws, pressure is measured in atmospheres. We know this. Right? Yes. So your standard atmospheric pressure is 1 atm or 760 torr or 760 millimeters of mercury or 101.325 kilopascals. Alright? So again, we have torr and your millimeters of mercury are the same value because you need this is the amount of pressure you need to support 1 millimeter of mercury in a barometer. This is why you have torr and millimeters of mercury are the same value. Here's some of our conversions. 760 torr is equal to 1 atm. 760 millimeters of mercury is 1 atm. 14.7 psi is equal to 1 atm. We don't really get too much into bar or kilopascals. Alright? Let's take some conversions. The gauge on a cylinder of compressed oxygen gas reads 1500 psi. Express the pressure in terms of atms, torr, and millimeters of mercury. 14.7. psi is equal to 1 atm.
14.7.
14.7.
102.04 atm. Okay. 102.04 atm times 760.
300 atms. 1500 atms.
Divided by 4.
I don't know if that makes sense. 1500 atms.
You said 1 psi is equal to 1
No.
atm, right?
No, 14.7 psi is equal to 1 atm.
102.04 atm.
102 atms.
And 77551.
551
torr.
77,501 torr.
And same thing millimeters.
Same thing for your millimeters of mercury. Do we get that? Do we need to do that? Okay. Boyle's law. Okay? Boyle's law basically describes the pressure and the volume behavior of gases when you are maintained at a constant temperature. You have your pressure and your volume is inversely proportional to each other. Charles looks at how your volume and your temperature is going to vary depending on if you maintain a constant pressure. Then you have Boyle and Charles and Gay-Lussac's combined together. This gives you the combined gas law. With the combined gas law, you take into consideration how your initial conditions, if you vary your initial conditions, how exactly is it going to end up at the end? Okay, your final conditions, how is that going to depend on your initial conditions? So you have the combined gas law, P1 V1 over T1 equals P2 V2 over T2. Here you have Gay-Lussac's. Gay-Lussac's takes into consideration pressure is directly proportional to your temperature. So P1 over T1 equals P2 over T2 at constant volume. Let's take a question. So this is for how are we going to recognize when we need to incorporate our combined gas law? No, specifically the combined gas law. What do you mean difference in temperature?
The pressure.
You will have two values for each. So you'll have two pressures, two temperatures, two volumes. This is how we know that, okay, we got to use your combined gas law. All right? So what is my initial conditions?
V1 is 2.5 liters.
Say it again.
Here the first volume is 2.5 liters.
V1 equals 2.5 liters.
Temperature T1 is 30.
T1 is equal to, how do we, with gas laws, how do we measure our temperature?
Kelvin.
In Kelvin. What is our T1?
30 plus 200 in the Kelvin.
30 plus
273.
273,
303 Kelvin.
303 Kelvin. P1,
1.8
1.8
atm.
ATMs.
T2.
V2,
You have to figure it out.
you got to figure that out. Your T2,
100 degrees Celsius.
100 degrees Celsius plus
373 Kelvin.
273,
373 Kelvin.
373 Kelvin. P2,
3
T2 is 3 atm.
how much?
3 atm.
318.
3 ATMs. So now we're going to solve for V2. If we have P1 V1 over T1, P2 V2 over T2, what does V2 equal to?
P1 V1 T2.
V2 is equal to
P1
P1
V1
V1
T2
T2
over
over
P2 T1 P2.
T1 P2. That's what I got to. So if we're solving for V2, what do we have?
We got 1.84.
1.85
85
liters. Again, so I'll plug in. Alright, Avogadro's law. So Avogadro came up with your ideal gas law that now takes into consideration the effect of the number of moles you have on the behavior of the gas when you vary the temperature, pressure, or volume. Alright? At standard conditions, standard temperature and pressure, which is 0 degrees Celsius and 1 atm, we know that our molar volume of a gas, meaning 1 mole of any gas at STP, will contain 22.4 liters. Did you get that? No? Yes? Yes, no? Okay? Now, ideal gas law. Our formula for our ideal gas law is PV equals nRT, where R is your universal constant, N is the number of moles, T is your temperature in Kelvin, volume, and pressure. The universal gas constant that we are going to use is 0.0821 liters ATM per mole Kelvin. Okay? Let's take a question. A 2.5 mole sample of gas is confined in a 6.17 liter tank at a temperature of 28 degrees Celsius. What is the pressure of the gas in ATMs? What do we do? Right? Same thing that we always do. What's the formula that we need? PV equals nRT.
0.0821, right?
Yes. What are they asking us to find? Pressure. How do we get pressure by itself? P is equal to nRT over V. Now, what is N?
Moles, 2.50.
2.5 moles. What is R? 0.0821 minus 2
ATM
liters
over ATM.
ATM. They know over ATM.
Over.
Yeah.
I didn't say over.
Yes, you did.
I said
Yes, you did. Per mole Kelvin. What is temperature?
28 degrees Celsius plus 273. We have to do that?
Yes.
Okay.
Which is
301.
301 Kelvin. What's volume? 6.17 liters. Yes.
How can we say degree Fahrenheit, degree Celsius, but not degrees Kelvin? Is Kelvin like from Mars or something?
You can say that. Okay? No, you don't. You love it. Okay, so again, now it's just to plug it in. Everything
And then divide by the
10.01 ATM.
10.01 ATM. You sure?
I did that in my head.
Is that in your head? I'm not sure what you said.
Alright, watch.
10.0. 10.0.
Oh, what happened?
Significant figures.
I can't get something right now. After rounding.
10.01 ATMs. Did we get that? Okay. Now let's take another one. Listen to what my question is asking you. Okay. A 4-gram sample of gas is found to exert a pressure of 1.71 ATMs when confined in a 3.6 liter container at a temperature of 27 degrees Celsius. What is the molecular weight of the gas in grams per mole? Lord. Okay, so now what's the first thing that we're going to do?
0.0821? Or is it 0.821?
0.08. You're going to find moles. How do you find moles? N is equal to PV over RT. What do we need? So we need our pressure, which is what? 1.71 ATMs. Volume? 3.6 liters. Temperature? 300? 300 Kelvin. and we have our R is 0.0821 liters ATM
That's
per
a
mole
4 gram sample.
Kelvin. Yes. So you find your moles. How much moles do you have? Hmm? Hmm?
0.2425.
Say it again?
0.25 more.
0.25 moles. Now what do I want my answer in?
Grams per mole.
Grams per mole.
It will be 0.25
So 0.25
over 4.
over 4?
Multiplied by 4.
Multiplied by
Yes.
4? No.
4 over point.
There you go. 4 is your grams divided by your moles, 0.25 moles. So what's my molar mass? 16 grams per mole.
Where you get that phone from?
I gave it to you in the question.
Oh, heard.
That's what I got to you.
Okay, so whatever answer you get, you divide it by.
Is it really?
Heard.
Uh-huh.
It's supposed to be oxygen.
Is that the mass of oxygen gas?
Oxygen.
Exactly. So that's not it.
Let's see.
Alright? Alright. So now, ideal gas law and density. Right? We can interchange these two to figure it out. You can find the density of your gas via your ideal gas law. Or you can find the whatever parameter you have for your ideal gas law if you know your density. Some things we need to take into consideration. In order to find moles, in order to find mass, sorry, you need your molar mass, okay? So you have moles multiplied by molar mass. What's the units for your molar mass? What's the units for your molar mass? Gram per mole. So if you have this here, you're going to get mass. So now, you can ultimately substitute your moles for what? What does moles equal to then? If we have this is true, how do you get moles by itself?
Mass
Mass over molecular mass.
There you go. Mass over molar mass. What is the formula for density?
Mass over volume.
Density is equal to
Mass over volume.
mass over volume. So if you now substitute this into your PV equals nRT, your ideal gas law equation. Can we get mass over volume? So if you substitute this into here, PV equals M over big M RT.
Transfer M on the left side and V on the right.
Not exactly, we still gotta do something.
And RT on the left.
You will P capital M equal to M over
PVM divided by RT.
P, V, big M
Divided by RT
divided by RT
equals to M.
equals to small m.
Now you can move V to the right side.
and now you divide V on both sides, and therefore mass over volume is equal to what?
Pressure
Pressure
times.
times,
Over the uniform.
times what?
More mass.
Molar mass over
Gas constant times
gas constant times temperature.
So, you're trying to say that density is also pressure times molar mass. Okay,
Yes.
that's cool.
Yes. So that's another equation that you gotta know. Alright? So let's take an easy question, the next question. Let's take this question. What is the density of carbon tetrachloride? What's the formula for carbon tetrachloride?
CCl4.
CCl4. Carbon tetrachloride vapor at 714 torr and 125 degrees Celsius.
So I turn this up 14 to 18.
You have to turn the 714 torr into ATMs.
714 divided by 760.
Yep. So what are the things that we need to know?
Molar mass.
We need the molar mass. What's the molar mass?
CCl4, right?
Yes.
CCl4, 45.5 times 4.
153.8.
150.8
328. Yeah. Gram per mole.
grams per mole. Very good. What's the pressure in ATMs?
0.93.
0.93.
9 or
0.94.
0.94. Yeah.
Gas constant 0.0821 liters ATM per mole Kelvin. Temperature
398.
how much?
398.
398
Kelvin.
Kelvin.
Now we can find the density.
So if we plug this in, what do we get? Density. And what does that equal to?
It's like next.
You tell me, you got a calculator.
Wait.
Huh?
Alright.
Four-
Got it.
4.42 gram per. This is gram per liter.
4.42
42
gram
gram per liter.
per
Liters.
liters. That's what I got too.
That's good.
Do we get that? Dronna, would you write it down?
He's so late.
Yes, you too.
Ah, there.
Oh, okay.
I always look at
Alright, so this next question is going to seem like it is a mouthful. But if we break it down into the tiny little steps, we should be able to get everything done that we need to. Alright? Here we go. A large evacuated flask. What does that mean? Empty. A large evacuated flask initially has a mass of 134.567 grams. When the flask is filled with a gas of unknown molar mass to a pressure of 735 torr at 31 degrees Celsius, its mass is 137.456 grams. What do we know about gases in containers?
It
Takes up the volume.
Huh?
Takes up the volume of the
That takes up the volume of the container. Good. When the flask is evacuated again and filled with water at 31 degrees Celsius, its mass is 1067.9 grams. The density of water at this temperature is 0.997 grams per milliliter. Assuming the ideal gas equation applies, calculate the molar mass of this gas. Alright? So, if we take this step by step, what are the things
flask.
The mass of the gas,
Oh, flask.
Of the flask.
what flask?
The vacuum.
The empty flask. What's the mass of that?
134,
134.567
567 grams.
grams. What else did they give us?
We have a pressure 3735 torr.
So your pressure is equal to
735.
735 torr,
0.97 atm.
which is equal to 0.7, no,
97
97.
atm.
Give me three significant figures, please.
9.67
967
atm.
ATMs. What else is given?
Temperature.
Temperature,
31 degrees Celsius.
which is
304 Kelvin.
304 Kelvin. What else is given?
The mass of the gas.
How do we find the mass of the gas though? We have the mass of the empty flask. And what else do we have?
We have the total mass of flask and the gas.
There you go. Mass of your gas and your flask, which is 137.456 grams. So therefore you can find the mass of the gas, which is equal to what?
2.889
2.889
grams.
grams. So that's one bit of information that we need. What else can we find?
We have the mass of the water.
We have the mass of your water plus your flask, which is what?
1067.9.
1067.9 grams. From this, what can we find?
Water. The mass of the water
The mass of the water.
is
Where
9.3.
did you get the 2.889 grams?
So we have the mass of the gas and the flask minus the empty flask.
Oh, so you subtracted.
Yeah.
Okay.
So how do you find the mass of the water?
Subtract.
Subtract the mass of the water in the flask
Which is 9.
from the empty one. So what's this? What's the mass of the water?
933
933.3 grams. From the mass of the water, what can we find?
The volume?
We can find the volume using, no,
Mass over density? Density.
using the density. So if your mass is 9 point, and your density,
0.997.
so what goes on the bottom? Your mass goes on the bottom for your density, which is 0.997 grams, 1 milliliter. So therefore, what is the volume of the water?
0.936 liters.
No, I got 936.1.
Thank you. 936.1
milliliter.
milliliters. What do we need our volume in? Liters.
So divide 1,000.
Divide by 1,000, so my volume is what? 0.936 liters. If your volume of your water is 0.936 liters, what does that also mean?
Gas volume.
It's the volume of your gas as well. Okay, so that's another bit of information that we need.
How did you get the mass of the water plus fast? You subtracted what?
The mass of the water plus the fast, that's given.
Oh, okay.
So therefore, the mass of the water alone, you can subtract that from the empty flask. So what's the formula that we need? What's the first thing that we need to find? So the density is equal to what?
or D?
No?
Or the other?
PM. Oh,
Pressure.
PM.
Pressure,
Times molar mass.
molar mass,
Over gas constant.
gas constant,
And times temperature.
times the temperature. Okay, so we have our pressure. We need to find our molar mass. We have our R, we have our T. Do we have the density of this gas?
No.
How do we find the density of the gas?
Uh,
Density is equal to mass
The mass divided.
over your volume. So what is the mass of your gas?
2.889.
2.889 grams divided by 0.936 liters. So therefore your density of your gas is
3.09
3.09
gram per liter.
gram per liter. So that's our final bit of information that we need. So all we need to do now is rearrange this.
And find the
How do we rearrange this? What do we need to do?
equals.
So we need the molar mass.
So it would be
So it's
DRT.
DRT.
DRT over P. So now we just plug this stuff in. So our density of the gas, 3.09 grams per milliliter. Our gas constant, 0.0821 liters ATM per mole Kelvin. Temperature, 304 Kelvin. Pressure, 0.967 ATMs.
79.7
79.75
gram per.
Gram per,
Mole.
okay? Same volume I have. Same density of your gas. 79.7 grams per mole. So again, you have this big thing, you just break it down into the little steps and you can figure it out. Take your time and figure it out. Okay, do not stress, do not get frustrated. Alright, Dalton's law of partial pressure. This is going to be the easiest thing you can learn all day. Right? Dalton's law of partial pressure, it simply means the sum of the pressures of the individual gases is equal to the total. So here, for example, you have gas triangle, gas circle, gas square. They all each have their individual pressures, and this is called partial pressures. When you have a mixture of these three gases, the sum of the partial pressure is going to equal to the total pressure. Alright, so let's take a question. You don't have to convert this. The sample of air is collected when the atmospheric pressure is 742 torr. The partial pressure of nitrogen and oxygen in the sample are found to be 581 torr and 141 torr respectively. Assume water vapor to be the only other gas present in the air sample. Calculate its partial pressure. So what's the total? What's the total pressure?
722. Oh no, 732.
742 torr. We have two partial pressures, 581 and 141.
722.
No. Okay? You add them up and then what?
Then this deduct from the 742. So we got 20.
So again, our total pressure, remember, total pressure is equal to the sum of your partial pressures. So your total pressure is 742 torr. Your partial pressure is 581 torr. 141 torr, and whatever your partial pressure of water is. So the sum of these two will give you 742 torr equals what?
722.
722 torr plus the partial pressure for H2O. You solve for H2O and you have what? You have 20 torr. Can we get that?
Yes, ma'am.
Alright. Here's another one. Partial pressure, the mixture of 6 grams of oxygen gas and 9 grams of methane gas is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas and what is the total pressure in the vessel?
P equal to M over V, right?
Huh?
The P equal to M over V.
P equals to M over V?
Mass over volume.
No? So this is partial pressure. So what are the information that they give you here?
Mass of oxygen, mass of methane.
So they give you liters, they give you temperature, and what can you find? They give you mass, what can you find with this mass? You can find moles. So therefore that is equal to the which equation are you going to use? PV equals nRT. So how many moles of oxygen gas do you have?
6 divided by 16.
No.
6 over 32.
32.
It will be 0.175.
You have to do 2 separate equations for oxygen, gas, and methane.
So how many moles of oxygen?
0.18.
1,8.
75.
8.
0.
Are we watching our significant figure?
Yes, of course you are.
0.19.
0.19.
It says 0.19.
How many significant figures do you need? 3.
0.88.
0.88. How many moles of methane do you have?
9.
9 divided by 6.
And over 16.
0.
16.
0.563 moles of methane. With this information, what are you going to do? Plug it into what?
The ideal gas.
Ideal gas equation. PV equals nRT. P is therefore equal to nRT over V. So the pressure for oxygen gas, the pressure for methane.
Okay.
0.188
8.
times 0.0821 273 over 15. Pressure
It's
for
0.98.
Is it undefined? Wait.
No, 2.
0.2.
Where do you see zeros? Like there shouldn't be any zeros here.
Oh, I forgot you had to convert it to.
Oh.
Pressure of oxygen is 0.281.
0.281 ATMs. And for methane?
0.841.
0.841 ATMs. And what about in total? You add it up and we get what?
1.122.
1.1
22.
ATM. So I got 0.281 ATM for oxygen gas, 0.841 ATM for methane gas. You add them up, you get 1.122 ATMs. Okay? Mole fractions. All mole fractions allows us to do is to be able to figure out our partial pressure without knowing our volume or temperature. Alright? Mole fraction. All you're going to do, the partial pressure is going to be equal to the moles of your gas that you're interested in divided by the total moles of your mixture times the total pressure. Do you get that? Okay. Here's a question for you. Don't let the fullness of the screen take you aback, correct? A study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole% carbon dioxide, 18 mole% oxygen gas, and 18.5 mole% argon. Calculate the partial pressure of oxygen gas if the total pressure of the atmosphere is 745 torr. So if we're using the mole fraction, what is the formula for your mole fraction?
P1 equals
N1
Over NT
over NT
times P
times PT, right? So we're ultimately looking for how many moles of your oxygen gas do you have? 18.0 moles. How much? What's your total moles?
80.
100 moles. 1.5 plus 18 plus 80.5 times what's your pressure?
745.
745 torr. So what is my partial pressure for oxygen gas?
134.1.
134.1 torr,
Yeah.
which is also equal to what? How much ATMs?
0.176
176
ATM.
ATMs. So I got 134 torr. Now let's take another question. If the atmosphere is to be held at 121 in a 121 liter space at 295 Kelvin, how many moles of oxygen gas are needed? So these two questions are connected. What is the formula that you got to use now? They give you volume,
Volume equals
PV equals nRT. What are they asking you to find?
N.
How do you find N?
And equals to PV over.
PV over RT. So now all we gotta do is plug this in. So pressure times your volume, which is 121, divided by R times T. Zero point 879 moles. 0.879 moles. Good job.
How many torrs equals to 1 one and.
760.
Sorry, what was it again?
760.
760.
760.
Okay.
Okay, we got 5 minutes. Most likely we're gonna have to finish this in lab.
How many slides is it?
Really?
760.
How many?
How much are we on now?
24.
24 to 30 something.
25.
You said
10
35.
slides.
We're using the ATM.
Yes.
Okay.
Let's finish it.
Alright? Kinetic molecular theory. Kinetic molecular theory simply talks about how the kinetics of molecules, okay, how are they going to interact with each other in a confined space. Alright? So we have some postulations in the kinetic molecular theory. Alright? Some of these things that you're going to see later on that they're not going to hold true. Alright? But for right now, they are true. Gases consist of large number of molecules that are in continuous random motion. The combined volume of all the molecules of the gas is negligible relative to the total volume of the gas in which the gas is contained. Meaning the gas is going to take up the container, take up the space of the container, so therefore we count them as the same. Alright? The attractiveness and the repulsive forces between gases are negligible.
Elastic. So it's elastic.
Elastic? No.
So you neglect kinetic energy, the transfer of kinetic energy within the walls of molecules.
For right now, this is under ideal conditions. We're saying that there is no transfer of energy. Alright? So here, the energy can be transferred in between molecules during collisions, but the average kinetic energy of a molecule does not change with time as long as the temperature of the gas remains constant. Now, if we bring this home, alright? Let's say you in your car and you post up at a stoplight, okay? Somebody coming behind you, they going too fast, speeding like a bat out of hell. They did not brake in time and they slammed into the back of you. What's going to happen?
Call the insurance.
You're not call the insurance, you'll get to that after. But what's going to happen to you?
Getting mad?
Your back is broken, you're going to move forward. Okay? Because the energy that the car was traveling was transferred to you, and therefore you go forward. Alright? What we're saying here, with molecules, if you maintain the same temperature, everything balances out each other. Okay? Now, when you add energy to your system, what ultimately happens to your molecules? They're ultimately going to move faster. So this is why the average kinetic energy of the molecule is proportional to the absolute temperature. So if you look here, your average speed of your molecule will increase if you have 0 degrees Celsius. It will increase as you raise the temperature to 100 degrees Celsius. We know this, right? So now we have